Okay, I think we should start. Welcome to the second session of the conference of the Kyiv-Leipzig mini conference. My name is Vitaly Kondorovsky, and I will be chairing this session. Before we will start, I would like to recall that each speaker has 30 minutes for their talk, including the questions. And let's begin with the first talk. It is my pleasure to introduce Yakubjan Kusanbayev, who will talk about some remarks on the asymptotic of the critical Galton-Watson branching process. Please, the floor is yours.
Thank you, Chairman. Consider a critical Galton-Watson branching process starting from one particle in the case when the number of immediate descendants of the one particle has infinite variance. We present some asymptotic results for the generating function associated with such processes. Let Xeg be a sequence of non-negative integer valued dependent and identically distributed random variables defined on a probability space omega fp. Each Xeg is distributed according to some common probability law pk, where pk equal probability X equal k. Let us first recall the constructive definition of the Galton-Watson branching process. A random process Z of n, defined by the following recurrence relation, is called a Galton-Watson branching process starting from a single particle. It is well known that this branching process is a homogeneous Markov chain. We can interpret Zen of n as the size of nth generation, where Xi and G is the number of the offspring produced by the G individual in the n-1 generation. The process Z of n is called critical if the expected number of offspring equal 1. It is widely recognized that many applet problems can be reduced to the study of Galton-Watson branching processes. The generating function is the main analytical tool for studying branching processes, and we will also use it in our investigation. Definition. A function defined by the following relation is called the generating function of the probability distribution pk, respectively of the random variable Xi. We define the iteration of the generating function of f of s by the relation. It is well known that the generating function fns of the random variable Zen of n is equal to fns. Therefore, by virtue of the continuity theorem, the k aspect of the asymptotic analysis of the random variables Z of n is the study of the asymptotic behavior of the iteration fn of s as n tend to infinity. The generating function f of s is called fractional linear if you have this presentation where bs more 0 and b more or equal 1 minus s. In this case, and the explicit form of the fn of s iteration can be found. It should be especially noted that finding an explicit form of the iteration Fn of S, except for some special case, presents a difficult technical problem. For this reason, there is a need asymptotic formula for Fn of S. Some important and well-known results. It is well known that is the case expectation Xi small or equal 1, the Galton-Watson branching process Z of n degenerated test with probability 1. 0 is an absorbing state of the chain. That is, Zn probability Zn tend to 0 equal 1. But probability Zn tend 0 equal limit probability Z of n equal 0. Therefore, an important task is to find the asymptotic behavior of probability Z of n equals 0. Obviously, probability Z of n equal 0 equal Fn of 0. Thus, the problem of finding the probability Z of n equal 0 is reduced to the determining the asymptotic behavior as n tend to infinity of the value Fn of 0 of the generating function Fns. Let us assume that f prime at point 1 equal 1 and f triple prime of at point 1 finite. Kolmogorov in 1938 proved that next asymptotic relation. Since the branching process Zn degenerates with probability 1, there is no point in the studying the asymptotic of the distribution function of the random variable Z of n. Applying Kolmogorov's result, we have for conditional expectation Z of n on the condition Z of n more 0 asymptotic relation. Next asymptotic relation. Therefore, it makes sense to study the asymptotic of the conditional distribution of Z of n under the condition Z of n положительно more 0. So Yaglom in 1947 proved that conditional distribution Fnx random variable this on the condition weak convergence to exponential distribution as n tend to infinity. Kestenier and Spitzer in 1966 proved that if the condition hold is satisfied, then the following relation holds uniformly for as from 0-1 interval. It is easy to see that relation 2 and 3 easy follow from relation 5. Indeed, putting S equal 0 into relation 5, we immediately obtain Kolmogorov's result. This means that for the Kolmogorov and Yaglom theorems to hold, it is sufficient that this condition is satisfied. For this reason, Atre and Ney in the monograph called relation 5 the fundamental lemma. For the sake of the completeness, we present the result of Fatou, which states that if this condition, third factorial moment finite, is satisfied, then the asymptotic relation holds. It is easy to see that from Fatou's result, easy follow the result Kolmogorov and Yaglom. And it is also follows that asymptotic relation. A natural question arises. If we have infinity variance, then there are any analogies of the obtained results. Now we will try to answer this question. For further exposition, we will need the concept of the slowly varying function in the sense of Karamata. Definition. A function L of x is called the slowly varying at x tended to infinity in the sense of Karamata if for any lambda positive L of lambda x over L of x tend to 1 as x tend to infinity. There are infinity many examples for slowly varying function. For example, next function is slowly varying functions, where Ki are constants, logarithm K of x, cut iteration logarithm of x. Well, let the generating function f of s have the following form, where alpha from 0-1 interval and fixed number, L of x slowly varying function at x tended to 0. Does such a function x exist? Yes, here is an example. This is. In this case, we have this double prime at point 1 equal infinity. The class of function of the form 7 contains the case this finite variance. In this case, alpha equal 1 and L of x tend this as x tend 0. It is well known that a slowly varying function L of x can be represented as where phi of x bounded measurable function on interval b infinity, such that phi of x tend to s, and tau x is a continuous function on b infinity, such that tau of x tend 0 as x tend infinity. Slack proved that if condition 7 holds, then the following relation true. This asymptotic relation true. This is analogous of Kolmogorov's result. Conditional distribution Fn of x, random variable, under condition Zn positive, weak convergence to f of x as n tend to infinity, where f of x is a stable distribution with density p of x, the Laplace transform of which has the form. This result is analogous of Yaglom's theorem. It is obvious that if alpha equal 1, then f at x is exponential distribution. The question arises, is there an analogy of the result of Fatou when this condition is held? In 2021, Chinese researchers Li, Zhang, and Zhang published a paper on asymptotic analysis of critical branching process with immigration, in which proved the following results for Galton-Watson critical branching process. Let the generating function f of s has the following form, where alpha and x fixed number, alpha from 0, 1 interval. So they are considering the case when phi of x equal s constant and tau t equal 0 in the representation function L of x. They proved the following result: uniformly S from 0, 1. This is a result is analogy Kesten-Spitzer results. And they obtain next representation, where epsilon and s tend to 0 as n tend infinity, and epsilon n equal logarithm n over n as n tend infinity. The authors applied the results to the study of the critical branching process with immigration stopped at 0. It seems to us that the class of generating function satisfying condition 10 is rather poor. What happens if we assume that S dependent from S? Whether relations will remain valid? Now we proceed to the formulation of our result. We introduce the following condition. Generating function f of s has the following form. Here, alpha from 0, 1 fixed number of s such that we need the following notation. According to Toeplitz lemma, from gamma n tends 0, it follows that big gamma n equal small o of n, and from delta n tend to 0, it follows that delta n big equal small o of n as n tend infinity. Theorem 1. Let condition A be satisfied. Then the following asymptotic relation is valid. Theorem 2. Let condition A be satisfied and delta n tend to 0, then uniformly for S from 0, 1 interval, we have next asymptotic relation and this presentation. Where epsilon Sn such that his supremum, this. If f of S constant, then phi n equal S, gamma n big 0 equals 0, delta n equals 0, then we get the results of the Chinese authors. Now we will look at the example. Example 1. Let f at S have this presentation, where alpha, this, where phi of x equal this. In this case, we have gamma n equivalent and this. This example shows that in the case of phi n no equal S, the remainder term can differ sharply from logarithm n over n. No, this is example 2. Let f at S have this presentation. In this case, we have S tend to 1, this presentation. In the this consideration case, gamma n equivalent 1 over n. Hence, gamma n big equal logarithm n. There. Another question arises. If the generating function has the form, this form, where L is the slowly varying function, then what is the analogy of the obtained results? I don't have an answer to this question. I can only say that when solving the problem, arise integrals looks so harmless of the type. The asymptotic behavior of the last integral may differ significantly from the logarithm n. There is also a dependence on the rate of the convergence of tau of t to 0. Now, I would like to briefly dwell on why I am interested in asymptotic relation of the type. First, the paper by Li, Zhang, and Zhang shows that such asymptotic formulas are important for studying branching process with immigration. One of the most important problems in probability theory, as is well known, is the problem of finding the rate of convergence in the limit theorem. In many limit theorems for branching process, the rate of convergence to the limit law is not defined. One reason for this seems to be the analysis of the generating function f n of S of the branching process Z of n. What do we know in this area? Nagaev Mohammed-Khanova in 1966 considered the critical Galton-Watson branching process, and under the condition of the existence of the third factorial moment, and proved that relation, where Fn of x conditional distribution Zn, E of x exponential distribution. When this result is obtained, the generating function f of s is expanded using the Taylor formula. The expansion for the generating function fn of s of the random variable Zn of n is established, and applied the well-known S-N inequality for the difference of the two distribution functions. Where t any positive number, f of t is the characteristic function of the distribution function f of x. As we well know, the Beer-Essen estimate in the central limit theorem for sum of identically distributed random variables has been studied in detail. It is probably appropriate to say that the accuracy of the estimate in 15 has not yet been found. Recently, several scientists have investigated the convergence rates in the Yaglom theorem and its analogies. For example, in the case the third factorial moment is finite, in the article of Pivkos-Rollin for critical Galton-Watson process, in the article of Carbona-Tabon, Jaramillo, and Palau for Galton-Watson process in the varying environment, using Stern's method, estimates of the rate of the convergence of the conditional distribution of Z of n, with appropriate normalization to the limit law obtained. In general case, when f of s have this presentation, random variable xi have no moment of the order higher 1 plus alpha, and we don't use Taylor's formula. A natural question arises: what is the rate of convergence in the above slack limit theorem? It seems to me that when solving this problem, the asymptotic relation can play an important role. It should be noted that the convergence of the distribution of the sum of independent random variables to stable law has been studied by many authors. Below is the list of reference used. Thank you for your attention.
Okay, thank you.
I finished.
Thank you for the interesting talk. Now we have 2 minutes for short questions. Okay, maybe I will ask the question. My question is the following: when you formulated your result about the generalization of the result of Chinese mathematicians, where you assume that the function f has some expression, including the function phi. Maybe you can propose an example of some distribution of integer random variables in Galton-Watson branch model, for which the generating function would satisfy that property. I just worry whether, I mean, this condition, how much examples it can be covered.
Мне нужен переводчик, конечно. Sorry, I am very bad at speaking in English.
Если... Хорошо, тогда I will ask very quickly my question in Russian. Мой вопрос
да.
был следующий. Когда вы сформулировали результат, который обобщает результат математиков с Китая, где у вас появлялась функция φ. Мой вопрос был следующий. Есть ли у вас примеры распределений случайных величин, для которых порождающая функция удовлетворяет это предположение?
Окей. Вот как раз вот у меня два примера. Если вы обратили внимание, вот в первом примере вот как раз альфа, где лежит между 0,5 и единица, получается, что гамма-n, вот как раз оно участвует, давайте вот это тоже сейчас посмотрим. Вот видите вот здесь?
Да.
Вот оно. Вот оно, давайте теорема 1. Вот здесь оно сидит. А пример показывает, что как раз гамма-n отличается от логарифма n. Вот пример. Здесь я как раз привел. Гамма-n является O большим n таким. Вот. И вот когда мы посчитаем, остаточный член уже совсем другое. Оно отличается от логарифма n, деленный на n. Вот как раз этот пример и показывает. А во втором примере уже все нормально. В этом случае оказывается остаточный член такой же, как это у китайцев. А вот этот первый пример показывает, что остаточный член может резко отличаться от логарифма n, деленный на n. Sorry.
Okay, thank you so much for your answer. Then we can so let me announce the second speaker. It is my pleasure to announce Naufel Salhiem. Naufel, are you here?
Yes.
Okay, maybe you should try to share your screen.
Okay.
Yeah. Now you can do that. Okay, very good. We can see your slides. Probably you can make the full screen.
Yeah. Okay.
Okay, and Naufel will tell us about some properties and asymptotics related to the generalized interaction local times of multidimensional Brownian motion. Please, Naufel, the floor is yours.
Thank you very much for the introduction. Thanks for the organizing committee for giving me this opportunity. As you said, my main object of consideration is the intersection local time of multidimensional Brownian motion. And let me start by a definition. Okay. So it's all about, BT is a d-dimensional Brownian motion, and it's all about this formal integral here, where delta u is a Dirac delta function at the point u from Rd, and we integrate this Dirac delta function from Bt minus Bs over S smaller than t in the time interval 0, 1. Of course, this is meant to describe the time so at S and t such that Bt minus Bs is equal to u. And when u is equal to 0, it describes the time such that Bt is equal to Bs. So it describes the time that the Brownian motion spends on its multiple points. Okay. Now, to give a rigorous definition to this formal integral, a first way consists on thinking about this Dirac delta function at a point u as a limit of the heat kernel. We know that this family of function here, this Gaussian density, it converges weakly when epsilon tends to 0 to the Dirac delta function at the point 0. So if we use this expression right here and make a limit, we, of course, provided that this limit exists at least in L2 sense. This will be a rigorous definition to this intersection local time of the Brownian motion. Another way consists on introducing first the occupation measure. So it is a random measure in RD, such that for every Borel subset A, the measure of this subset A it is given by this integral, and it computes exactly the time SNT such that the increment BT minus BS belongs to A. And then it is enough to take the density of this measure. So if this measure has a density, almost surely, and this density, it is preferable to be to have a continuous version, and then the value of this density at some point u will be will represent the intersection local time at the point u, which we denoted by rho 2 of u. Of course, this it depends on the dimension, so that this measure has a density or not. To see that both definitions coincide, it is enough to use the following occupation formula. This formula tells us how to integrate a function with respect to this measure, to the occupation measure. And if this measure has a density or ρ2, then the integration of a function with respect to ρ2 has also this following expression. It comes easily from the definition of the occupation measure. If we take as phi instead of the function phi the heat kernel that we introduced in the first slide, then we can recover by the properties of the heat kernel, we can recover that ρ2 coincides with the first definition. Okay. Now, why does the intersection local time of the Brownian motion matters? Why is it important? I will cite first one physical application, and maybe later I will come back also to another application, but from a mathematical point of view. Okay. The physical application is related to polymer models. A polymer is a long linear molecule which consists of a huge number of small blocks, maybe atoms, maybe small molecules. They are always called monomers, and which are linked chemically one to the other. I say a huge molecule because it consists usually of tens of thousands of these monomers. And we know too many examples in our real life, the DNA in our cells, for example, the protein, and the chemical components of most of the plastic devices. Okay. Now, which mathematical model can we associate with polymers in order to study them? If we have a closer look to a polymer, we can have this kind of pictures. And you see that the shape is random, and this randomness comes from at least two different sources. There is the random media surrounding the polymer, and also there are the interaction between the different monomers that are in the polymer, that constitute the polymer. And when a mathematician looks at this picture, he may think to a random walk, he may think about a Brownian motion, and probably more generally about stochastic process. So the main models associated are random walk and the Brownian motion. But still, there is a small problem. We know that trajectories of random walk and trajectories of Brownian motion and at least in dimension 1, 2, and 3, they have multiple points. They have multiple points, but if we consider a real polymer, we cannot expect it to have multiple points. We cannot expect two monomers to occupy the same space. This is called the excluded volume effect, which does not allow self-intersection. And we can imagine a monomer as a small ball. And we know that if we have two balls, then their centers are always separated by a minimal distance equal to the sum of the radiuses. So this excluded volume effect, which comes from the physics of polymers, now it becomes problematic when we have ideal polymer, which is a random walk or a Brownian motion. So to solve this, it was proposed to make a penalty or use this weight here, this exponential function, where in the exponent we have minus beta ht. The beta is a positive constant called the strength of self-repellence, and this ht is given by this integral, and we can recognize here the intersection local time of the Brownian motion. So why do we use this, and why would you call it a penalty? If we have a trajectory of the Brownian motion which spends too much time around its multiple points, then we expect this integral to have, this formal integral to have a high value, but taking this expression, we can reduce that high value to 0. But if the trajectory of the Brownian motion spends small amount of time around its points of self-intersection, then this integral is expected to have a small value, and this weight here is closer to 1, so it does not affect anything. So this is the penalty. This exponential function is used to construct, is the main expression in the polymer measure, which is a measure on the space of trajectory, the Wiener space, and it is a measure that gives more value to those trajectories with less self-intersection local time, and which reduce the value of trajectories with more self-intersection local time. Okay. Now let me go back to our object of consideration, and let me recall some known result about the existence and some properties of the intersection local time of the Brownian motion. In dimension 1, it was proved nearly one century ago that this intersection local time exists at any point from the real line, and this intersection local time depends continuously on this u. It was the same thing in dimension 2 and 3, but rho 2 of 0 does not exist, and rho 2 of u, it blows up around 0. It has an infinite limit when u tends to 0. Okay. In higher dimension, this limit, this intersection local time does not exist as according to our any of the both definition given in the first slides. And next, there were some description of this behavior of this intersection local time around 0 in dimension 2 and 3. In dimension 2, Varadan proved that if we subtract from rho 2 of u this logarithmic expression, which is in fact an equivalent expression to the expectation of this intersection local time. So if we subtract this and make a limit to 0, then we will find the finite limit. So row 2 of u behaves around when u tends to 0 in this logarithmic scale. The same finite limit can be obtained differently in this way. And it is called renormalization, Faradana renormalization. And in dimension 3, quite similar renormalization was done, but a little bit also different, because it was not enough to subtract the expectation of this intersection local time in order to have some finite limit. We need also to divide by this logarithmic square root of this logarithmic expression in order to have a finite limit in L2 sense. This is like a central limit theorem. And the limit is, in fact, a Gaussian random variable. Okay. We wish to make similar things in higher dimension, even though the intersection local time, as I said, does not exist in higher dimension. For this, we will introduce Sobolev spaces. But first, we need to recall the E2 Wiener expansion of a random variable, a square integrable random variable, which is measurable with respect to the sigma field generated by the Brownian motion. The E2 Wiener expansion is an expansion into a series of multiple E2 stochastic integrals. I will denote them just in this compact way, Ek of Fk, where Ek denotes a k multiple E2 stochastic integral, and Fk is a deterministic square integrable kernel. This series converges in L2 Okay, now using this structure of this L2 space, we will construct the Sobolev spaces of a Wiener space. The construction is here given in some algebraic way. The idea is to complete the following subspace from L2. It is subspace which contains random variable with a finite number of E2 integrals, and we complete this space with respect to the following norm. And the result is a family of these Sobolev spaces with the following hierarchy. The more the gamma is positive, the smaller the space is, and we have this inclusion. If this index gamma is negative, then we have larger space than this L2 space of Wiener square integrable random variable. Of course, they are called Sobolev spaces because they are also intimately linked with the differentiability. In fact, when gamma is a positive integer, then D2 gamma is exactly the space of square integrable random variable, which are gamma times differentiable, and all their derivatives are also square integrable. We also have some norms which are defined by the stochastic derivatives and are equivalent to this norm. For this reason, by the way, the gamma is called the differentiability index, while the 2 is called the integrability index. Okay. The intersection here of all those spaces is called the space of Wiener test function, denoted D2 plus infinity, and the union of all these spaces called the generalized Wiener, the space of generalized Wiener function. And we have duality relation between D2 minus infinity is the dual space of D2 plus infinity. We have this basic result, which tells us that this limit, which does not exist in the usual L2 sense, now it exists, but in a larger space than the L2 space. In fact, it exists in the D2 gamma, in the space, Sobolev space D2 gamma, for each gamma which is smaller than 4 minus D over 2. You see here that if D is greater or equal than 4, then this gamma is a negative index, and so this D2 gamma is larger space than usual L2 space. So if the limit did not survive in the L2 space, but the good is that it survived in some larger space than this L2 space. This result is also true for D equal 1 and 2 and 3, but here I just wanted to concentrate in higher dimension, D greater or equal than 4. And also a good thing when we apply this to D equal 1, for example, we will find that this gamma is should be smaller than 3 over 2, and particularly in dimension 1, this intersection local time belongs, if it belongs to D2 gamma for gamma smaller than 3 over 2, then particularly it belongs to D2 so it is stochastically differentiable. However, in dimension 2 and 3, it is no more differentiable. So those spaces and this result give us an idea about the differentiability, the regularity of this intersection local time. In the same, maybe in the same context, some other results discussed the existence of intersection local times of some stochastic processes as element from these Sobolev spaces. And I can say that this became a trend for maybe the last 30 years. Okay, I just have chosen 2 results to cite here, not all of them, of course. So this result, for example, it tells us, it gives a condition on the Earth parameter of the fractional Brownian motion, and such that under fixed dimension D and fixed positive alpha, under this condition, we have that this renormalized self-intersection local time, it belongs to the space, Sobolev space D2 alpha. So if we want to know when this renormalized self-intersection local time is, for example, differentiable, we should take the alpha equal to 1 and see for which h do we have this. Of course, this will depend also on the dimension D. But if we want to have to see when do we have more regular renormalized self-intersection local time, which means that we want to have the alpha bigger, then of course, as you see from here, the h will be smaller and smaller. And when the Earth parameter is getting smaller, it is known that the trajectories of the fractional Brownian motion get more irregular. So from here, we conclude that when the intersection local time becomes more regular, this reflects that the trajectory of the underlying process get more irregular. And we see that the regularity and this go in opposite direction. And this is the second application of self-intersection local times, but this is from maybe more mathematical point of view. Okay, in the same context, I would like also to mention the result by Alexei Rodenko, which it can extend the last result by Hu and Mueller. Okay, this is a more general setting. He considered a Gaussian random field, a centered RD valued Gaussian random field, considered integrals of this type. So where P epsilon D as the heat kernel that we are using, and EXI if T is the Gaussian random field, and here nu is a measure on the set T. Okay, of course we can include our the intersection local time in this in this framework, because it is enough to take xi, the random field xi as b of t minus b of s, or x of t minus x of s. Okay, so he gave some equivalent condition which ensure that this kind of integrals has a limit in a Sobolev space D2 alpha, and this is for a fixed alpha. Okay, and through this result, he even got better results than the one described here. But when he takes an interval of time which does not include 0. Okay. Okay, now let me go back to our object of consideration, and we go back to our generalized intersection local time. We said that in dimension greater or equal than 4, it only exists in the Sobolev space D2 gamma for gamma smaller than a fixed threshold. Okay, now we will use the following theorem, which due to Sujita. It tells us that if we have a generalized Wiener function, which is positive in the sense that whenever it is tested against a positive test function, it gives a positive result. Such positive generalized Wiener function can be represented by a measure on the Wiener space in the following way, that the representation is given in the way that testing phi against a cylindrical test function can be written in an integral way, an integral against with respect to this measure. So let us apply directly this result to our generalized intersection local time. We got this result. So we are again in dimension greater or equal than 4. We are considering this limit, which only exists in some Sobolev space with a negative gamma. So it is generalized Wiener function, and it is positive because it is a limit of obviously positive random variable. Consequently, we can associate to it a finite positive measure on the Wiener space. And this association is explained in this integral. Now, if we want to discuss properties of this generalized intersection local time, it is enough to look at this measure, theta u. And we are trying to describe this measure and see some asymptotics, some properties of this measure. First of all, this integrating a cylindrical test function with respect to theta u. Okay, of course, we are this measure is a measure on the Wiener space, so the integral looks a little bit complicated, but we can give it a more appropriate another appropriate representation, which is given by the following integral. It is enough to integrate over s smaller than t. Take the conditional expectation of this test function with respect to bt minus bs and evaluate it at the point u, and then integrate it with respect to this Gaussian density. Okay. If we have now this integral formula, then we can apply it in a very simple way. Just take this test function to be equal to 1. And then we will see that we have, of course, if you put 1 here, you will have the theta u of the whole Wiener space. And we will get from the other side this integral of this Gaussian density. And we have some asymptotics for that. Okay, probably I can say that this, in some way, it looks like the renormalization in dimension 2 and 3. Okay. Let me continue with another theorem from Sujita, which tells us that any positive generalized Wiener function, of course, we said that it is always such kind of function is associated with some positive finite measure on the Wiener space. it happens that always those measures have a Fernic type theorem. And consequently, our measure theta u has also a Fernic type theorem, and at least this will tell us that it has finite moments of any order. Okay. Here we define a probability measure from theta u by just dividing it by normalizing it. Okay. Next, of course, we know that we already have a very nice measure in the Wiener space, which is the Wiener measure, which is a Gaussian measure. And we are trying to estimate the distance between this measure, our measure, new measure theta u, and our Wiener measure. Okay. Of course, the quadratic Wasserstein distance will need, in the definition, we need to have coupling in the product space in order to estimate this, the quadratic Wasserstein distance. To avoid this, we thought about using a Talagrand inequality, which is an inequality between quadratic Wasserstein distance and relative entropy of probability measure. But this only happens in, this is only stated in finite dimensional spaces. So for this, we will look to the finite dimensional marginals of our new measure theta u, and of course also our Wiener measure, which we denote by mu, and then we will measure the quadratic Wasserstein distance between them. Let me recall the relative entropy will appear in the Talagrand inequality. If we have two probability measures on the same probability space, then the relative entropy of one of them with respect to another, this is not a distance, it is not symmetric. So h of nu1 with respect to nu2 is the following integral, and here we have the logarithm of the density of nu1 with respect to nu2, and then we have to integrate with respect to nu1. If there is no density of nu1 with respect to nu2, then this value, this relative entropy is assumed to be infinite, and the minimal value of the relative entropy is equal to 0, and it only happens when nu1 is equal to nu2. In some sense, the relative entropy measures gives more value to probability measures which are very different, more different. Okay. Now the Talagrand inequality between two probability measures on Rn is the following inequality, but we suppose that the measure nu2 has a density with respect to the Lebesgue measure, and this density can be written in this form with the V infinitely differentiable. We also suppose that the Hessian matrix of this V has a positive smallest eigenvalue denoted by kappa, which will appear in this inequality. So we will try to apply this for nu1 and nu2. Nu1 will be the finite dimensional marginals of our new measure theta u, and the nu2 will be corresponding finite dimensional marginals of the Wiener measure mu. Okay, now let us define those finite dimensional marginals for the Wiener measure mu. So we'll define mu n as the following measure. So mu n of a Borel subset from Rd times n will be the Wiener measure of those trajectory such that this vector belongs to A. In other words, this is exactly the distribution of the random vector b1 over n, b2 over n until b of 1. B is always denotes always the, of course, the Brownian motion in Rd. We know very well this measure, and we know even its density with respect to the Lebesgue measure. It is given by this formula. And we will try to do the same with this uniform partition of 0, 1, we will also construct the finite dimensional marginals of measure theta u. So we define theta u n as a measure on RD times n in the same way. And one can check that theta un has the same.
No, Fede, I'm sorry to interrupt you, but we are out of time. It would be nice if you could go to your final or to your main result to present
Okay.
it.
Okay, thank you.
Thank you so
for
much.
letting me know. Okay. So here we have the exact density of the explicit density of theta un with respect to mu n. So we have the exact expression of this density, which will appear in the relative entropy. And from that point, we can estimate the relative entropy of these marginals of theta u with respect to the marginal of mu. And we have this, it's a little bit rough, but as a first result, it is good to start with. And now we need this kappa, constant kappa, which should be extracted from the Hessian matrix of this part in the exponential form of the measure mu n. Okay, so we take the Hessian matrix of this part in the exponential, and we have the Hessian matrix, and we get explicitly the eigenvalues, and the smallest one is given explicitly by this. Now it is just enough to write the Talleyrand inequality, and we obtain this estimate right here. Okay, this is my last result. Thank you very much.
Thank you, Nofel, for a very interesting talk. And we have time only for a very short question. Okay, maybe I ask a very short question about, can you say about the normalization, is something known in the dimension, say 4, 5, and so on, where you can also renormalize at 0 and get something non-trivial, but in the space of Sobolev functions? Like the results that you presented in dimension 2, where you subtracted the expectation, dimension 3, where you divided, but now you have new spaces and
yes, actually I don't know really similar results in higher dimension, but probably this one may be first can be considered as
okay, I
first
see.
renormalization.
Yeah, I see. It is like the first step.
Yeah.
That direction. Okay, thank you so much once again. And now so we will have the third speaker, Hennady Navrotsky. Hennady, can you share your screen? I saw you that you are here.
Yes.
Oh, okay, very nice.
Yes.
No, we cannot see it. Now we can see your screen. Please, like make the full screen presentation. It is Ctrl L.
Thank you. So yes, so
yeah, okay, we can see it. Okay, then it is my pleasure to introduce Hennady Navrotsky, who will talk about the winding number of the Gaussian random field along the planar curve. With Hennady.
yes, thank you. So the main object of our study is the random Gaussian central stationary random field defined on some compact B, which is a subset of plane R2. So then our goal is to calculate the winding number of the field and its asymptotics along this boundary. So this the covariance of the components of this field is equal to the exponent minus square u minus v squared, and its components are all centered and dependent for different components. And since our covariance function is infinitely differentiable, the components xi are also infinitely differentiable. So yes, then we define the winding number of some continuous vector field xi on the continuous curve, which is parameterized by the interval 0, 1 as the number, the difference between 5, 1 minus 5, 0 divided by full rotation, which is 2 pi, where pi is the continuous branch of the angular function. It is also clear that the angular function doesn't change when we divide or multiply all the vectors, the field by the same number. So the winding number also doesn't change. So as an example, we can with the vector field on the plane, we can look on the following vector field, which its x components equal to x squared minus y squared, y component equal to squared plus y squared. So if we try to calculate the winding number on a unit circle, it will be equal to 0. Well, why? Because square plus y squared is always equal to 1. Therefore, there is no such point circle where there is no 2 points on the unit circle where the corresponding two vectors will point in the opposite directions. So, since squared plus y squared is always non-negative, then our well, y component will always be non-negative. Then yes, you can conclude that it will be always that the winding number on any closed curve will be equal to 0. Yes. Further, we have result of Adler-Taylor on the page 268, the random fields and geometry, which is that for a standard random field defined on the closed domain, if the field is if the covariance function of the field is twice continuously differentiable, then we have continuous modification. Moreover, for any natural and for all epsilon, we have the following condition of the modulus of continuity. So further, in order to calculate the winding number of our Gaussian random field, we use the cross-necessity formula for the deterministic vector field on the boundary of some compact V. So the winding number of the deterministic vector field on the boundary of some complement B will be equal to just the sum signs of the determinant of a matrix of all partial derivatives of the vector field. Yes, and it is taken in the sum is taken over all points such that a vector field is equal to 0. So yes. Next, we have the following Katz's formula for fixed for the expectation of the winning number xi on the boundary of some compact B. Yes. So, and there are in the work of Kuznetsov A.V. Were found the sufficient conditions for this formula to hold. So, summarize as so that for any for all components of F, the components Fi and their the vectors of their partial derivatives nabla Fi must be well, the distribution must be non-degenerate, and the probability density must be continuous in X equal to 0 for all T, and the conditional probability density for components f of T conditioned on the condition on the partial derivatives number f of T also exists, is bounded, and is continuous in point 0. So, and then we have also the condition on the models of continuity, which our field satisfies because well, which each Gaussian field is twice differentiable covariance function satisfied by previous theorem. So, yes, and in order to use the Katz's formula, we need to prove the following: that the probability that there is such U from B that psi of U equals to 0 and determinant of the psi prime of U equals to 0, such probability is equal to 0. So the method of proof is similar to that used in the paper by A. Durogovtsev in the paper on a stationary random knot. So first we define the function which is just the indicator of ball with radius epsilon, then the integral, then when epsilon converges to 0, then it must well converge to just the area of B, the density in the point 0. So yes, so then we assume that we have such random events that probability is positive and psi of U is equal to 0 and determinant psi prime of U is also equal to 0. So then we can calculate such an integral. Yes, we calculate such an integral on the yes, on the event A. Then it will be equal just the area of pre-image or ball with radius epsilon. Then we can calculate the point U, the area of pre-image of such a ball as the epsilon. So since our derivative on one of the vectors, our derivative must be equal to 0, then we can see that it's will be an ellipsis with so area proportional to epsilon to the power of 3/2. So then we can see that the area of preimage circle greater or equal than some constant, than some number dependent on the omega, the epsilon to the power of -1/2. But then converges to infinity, so we obtain a contradiction. Yes, so further we try to prove the Katz-Rice formula for our case. So for that we simplify by writing this the difference of two numbers, which is gamma plus and gamma minus, where gamma plus just the number of such u means that the determinant is greater than 0 and xi of u is equal to 0. Yes. So for that we define also introduce also two additional functions, which is f of x, alpha of x, fn of x, and gn of x. And so the idea is to define fm and gn of x such a way that this sum q and m will be just converge to sum of the indicators of determinant xi of s is greater than 0 over all points s such that xi of s equal theta. T is some arbitrary number. So then we prove we can just take as the arbitrary continuous function with compact support and apply the area formula. So then since yes, then we need to obtain a bounded function, and then we just take the limit over m and n. Since this equality would hold for any continuous with compact support, then we will hold almost surely. So we obtain our result. Yes, so the next, how do we apply this formula is the Katz-Rice formula. So one of the results is that the expectation of determinant psi prime x condition of xi of x equals 0 will always just be equal to 0. Why? Because they are independent, which is the partial derivatives from xi of x. And so we can conclude that the winning number is always equal to 0, and the expectation of the winning number is always equal to 0 on any boundary of the complex R2. So in the next, we can use the stationarity for random field to prove that the expectation is always doesn't change under any shift as in R2. For that, we just use just change the variable for which we integrate. So that's all, I think.
Okay, Hennady, thank you for your talk. And we have, as I understand, you finish, right?
Yes.
Okay, now we have some time for questions.
Maybe I have a short comment. In my opinion, this asymptotics is a preliminary result for understanding of topological structure of the random knot, which we obtain as in a three-dimensional image of such circle. Of course, this Weiden number will be responsible for some of topological characteristics, but not for all. So we are trying to do this step by step, and I hope that Gennady will present next talk next year with another characteristics. Okay,
Thank you.
thank you.
Okay, if it is not the case, then Gennady, thank you so much once again. And the next talk has to be started in 5 minutes. Should we wait, since it is already last talk, should we wait 5 minutes?
I think that we have to be on schedule.
Okay, very good.
So let's wait.
Then let's wait. Okay, it is my pleasure to introduce the last speaker of our session, Maria Belozerova. She will talk about SDE with interaction on the Riemann sphere. Please, Maria.
Thank you. Thank you very much for the opportunity to have a talk on this conference. Now exactly I have problems with. Okay, maybe I need to have a little presentation because
please.
Because it is a lot of problem with my presentation in a good size. Maybe this is because of my computer. Wait a minute. I will try to share this. Oh, okay, now I can share. Maybe now you can see the presentation.
Yes, thank you.
The behavior of the flows or the mass distribution on the sphere is important because, for example, if you consider the flow of the weather flow on our Earth, we can see that here can be not only rotation of the mass, but also we can see here a red attractive set for these flows and also blue attractive sets and so on. So this is important to study such a flows. And let us first consider ordinary differential equation 1 and here f is continuously differentiable function And let us consider solutions to such equations. And our goal is to understand how will be the evolution of mass by the flow that is defined by this differential equation. Firstly, let us recall what is the behavior of solutions to such equation, and what is the behavior of integral curve to such equation. Let us recall that what is the equilibrium point of system 1. That is such a point that our derivative equals to 0, and therefore we have always the solution x equals this x0 if x0 is a critical point. Also, let us recall with our picture cycles, and what is in general cycle. This is some periodic orbit of some solution curve. A periodic orbit gamma is called stable if for each epsilon greater than 0 there is such neighborhood y, that the distance between our solution phi and this y tends to 0 for a large t. Now, what kind of results we can expect, and also what we know about our solution curves. On infinity, that can be the next situation. If we have a limit as tn tends to plus infinity, you have some limit pi, then we call such a point omega limit point. If we have here, okay, and if we have a limit point as t tends to minus infinity, then we call such a point alpha limit point. And also the sets of omega limit points we call omega limit sets, and the sets of alpha limit points we call the alpha limit points. The next theorem of Lorentz-Perka tells us what can be the situation of these alpha and omega limit sets, and the alpha and omega limit sets of trajectory gamma of the system 1 are closed subsets of our set E, and if gamma is contained in compact subset of Rn, then alpha from gamma and omega from gamma are non-empty connected compact subsets of E. And here we see the example of flow, and later I will show you the exact differential equation for this picture. And here we see that the gamma is omega limit set for curves above and below on the picture. This theory is good established on manifolds. Let us consider Mn a differential manifold, and then a vector field of class CR on this M is a CR map with associates a vector field, and this corresponds of the map from M to Tm, and we denote XR at M the set of such CR vector fields on M. And an integral curve of this x that goes through a point P, map some interval into M. So we consider curves and solutions to systems on the manifold M. And the image of this integral curve is called an orbit or trajectory. To understand the behavior of solutions to systems of ordinary differential equations on the manifolds, very important is the next theorem that show us all possible possibilities that can happen with curves of these integral curves as t tends to infinity. So let x our solutions are on the M, and M is a compact manifold, and P is on M. Then the omega limit set of this P is non-empty, closed, and invariant by the flow of X. And it is connected. If the omega limit set of a trajectory gamma doesn't contain singularities, then this omega limit set of gamma is a closed orbit, and the orbits through points close enough to a point pi of gamma have the same closed orbit as their omega limits. Now, what can exactly be this omega from pi? The famous Poincare-Bendixson theorem tells us that our omega from pi is or a singularity or a closed orbit, or consists of singularities P1, Pn, and so on. That satisfies the next condition. So this here are considered all situations that can happen with our trajectories. And now our goal is to understand what can then happen with some mass that is distribution on the manifold. And today I consider Riemannian sphere. And firstly, I want to show the example that a small example. What about the curves on sphere? This is a differential equation 2, and this is a phase portrait of solutions to such system. And we see here the limit set gamma, and this will be closed orbit. And also the question of the point of my work is to understand what is the mass distribution as time t tends to infinity on the sphere if we have the first mass distribution, and then what happens if also you have a flow on the sphere. This is some literature about dynamical systems, and where we can read some information about the behavior of solutions to differential equations on some manifolds. My goal is not only to consider the ordinary differential equation, but further to consider the stochastic differential equations with interaction that was proposed of Anatoly and have the type 3. But this The question of behavior to measure value solution mu t is considered of Andrei Anatolievich Strogovtsev and his students, and they proposed in his works with Maria Karlikova the next definition, the shift compactness, and to study the behavior of this MUT. And we call the set of measures mu alpha to be shift compact if for all alpha there exists some vector u alpha in RD such that the set of measures of mu alpha minus u alpha is compact in the set of measures MN. So this was so an approach to consider what happens with this mu alpha, but my goal, and this is result of Andrei Strogovtsev and Maria Karlikova. What happens? We have the equation 4, and let mu0 has a finite 2n plus 2 the moment, and phi satisfies the condition 5, and B satisfies Lipschitz condition on X, and mu with constant B, and let also we have the condition 6, and then the set of measures mu t is a shift compact. But my goal is to get results for stochastic differential equations with interaction of the type 7. If, for example, this mu t lives on Riemannian sphere. This is the first step of my work, but the previous step is to consider ordinary differential equation and solve the problem for ordinary differential equation and mu t. Let us consider a small example, 8, and let us consider mu t and some mu0 distributed on Riemannian sphere. Let us notice that if we live on this Riemannian sphere, then all curves of such a system 8 lives on this sphere all the time, because the derivative here equals to 0. So this is a system that we can solve and consider the exact solution. This is of such a type, and also we can calculate the critical point that have the next type for some t. Maybe it will be better to write t0, and so we understand that our critical points are on poles on the sphere where we start to consider solutions. And also because of our calculation, we see that our integral curves are circles that are perpendicular to the vectors with coordinates 1, -1, -1, and also lies on such a plane that they have equation 9. So our solution just make a rotation in such a planes as t tends to infinity. So what can happen then with our mass distribution? Let us consider two small examples. First example, if mu0 is some delta u0, so if we have one point of our sphere, then we understand that just this point just rotate on our sphere, and that's all. and therefore we have answer, and we can write exactly our mu t. A second example is if our mu0 is uniformly distributed on our S2, and then we can calculate and understand that the mu t is also uniformly distributed on S2. But our goal is to consider more general case. Firstly, let us consider the system 10, and the idea of the results X is the next one. Suppose that we have the situation like it was in the example this one. Suppose that we have exactly one limit and limit circle gamma, and all the trajectories tends to gamma as t tends to infinity. Then we understand what happens with our mu t, and in the sense that if the set A is sufficiently far from our gamma, then for large t, our mu t from A just equals to 0. And here are the conditions that we can't to be close to our critical points. And the next, and also this is just a first result, because my goal also is to consider all the situations what can happen on the sphere. But another step is to get something about differential equations with the interaction. And the idea is the next one. Let us consider our system 10, and then let us do the time change that you can see on this slide. And then it is known that we get exactly a differential equation with interaction of the time 12. And let's notice that using this time change, we get the same trajectories that was for equation 10. Therefore, we just change the time with, and then we change the velocity. We are moving on these trajectories. And therefore, the result about the MUT we can get.
Maria, excuse me, and phi, is it positive function?
Phi?
Yes.
Yes, phi is positive.
It must be positive. Okay, thanks.
And then we have that from previous lemma, we get also by such a conditions of our right side of 10 that we have the similar results for large t. This is just a way what we can do, but later we will consider all the situations on sphere and try to remove something to stochastic differential equations with the interaction. Thank you very much, and that's all.
Thank you, Maria, for your interesting talk. And now we have enough time for questions.
Okay, also let me make a comment. We already discussed today that the space of measures, even on one-dimensional circle or even on the interval of the real line, is infinitely dimensional, has a complicated structure. So when we consider the flow on the space of measures, it can have properties very surprising comparatively to the finite dimensional flows of dynamical systems. But still, since equationless interaction give us a very degenerated flow, There exists a hope that it will inherit some properties, some geometrical properties, which we face already. So it looks like we can have something like Poincare-Bendixson theorem when we have equationless interaction, and we have a flow related to this equation in the Wasserstein space. This is our goal. So we want to look at equationless interaction as a dynamical system in this Wasserstein space, and then try to make more or less the same classification, at least for simple flow, as in Poincare-Bendixson theorem. So I hope we will continue this work. Thank you.
Thank you, Andrei Anatolyevich. Other questions?
I mean, Andrei just said what I was going to ask, because what we saw is just a preliminary step. But basically, if you study such dynamical system as Andrei Anatolyevich was just saying, on the sphere, the probability measures on the sphere is a compact space. So you would expect that in some sense you would arrive at a similar result, right?
Yes.
But
Exactly.
the question, what regularity means in this concept? What is a vector field and all this? This is not so. This is some details which one has to work on, right?
Yes, but my idea is following. Do not look about a general condition on the flow and dynamical system. Let's look for flow generated by equationless interaction.
Yes,
Then
yes.
we already have some regularity, we have some degeneracy. So
Yes.
at least in this case, we want to get such classification. Yeah.
Okay, good. More questions? Okay, if it is not the case, then Maria, thank you once again, and also thank you to all speakers. And it was last talk. Probably Andrei Anatolyevich, you want to say something at the end?
Yes, for today we finish our job, and hope today we have another fruitful day. So today we start at 12 in Kyiv time. See everybody tomorrow. Yeah.
Yeah.
Bye.
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 Thank you. Bye.
Thank you. Bye.